All right, hello everyone. Welcome to another episode of Quirkcast. This is your host Tim.
I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. Before we get started, if you're on YouTube, please do ask us any questions that you might have during the episode so we can get to them. Also, if you haven't joined our Discord channel, and in addition to that, more guilt tripping, do leave us some X number of star review for wherever you listen to your podcast and leave feedback. So that would be incredibly helpful for us. And without further ado, let's get started. So I guess Tim, I was thinking that like when I was last studying particle physics, I was talking about going to some fundamental scale and uncovering the fundamental quote unquote truth of the universe. So I wanted to ask you, like, does that actually exist?
That's a that's a really deep question, I think, and also quite complicated. I think there's a reason why this thought is so ingrained in kind of a particle physicist's mind. I mean, after all, our field, particle physics, is called fundamental physics. Like it's in the name, and I think part of it is his historical, right? Like we always have this framework of thinking about like through history we study things, we study objects by thinking about its constituents, right? Like metal or piece of wood, or the human body is made of something smaller, and ultimately those something smaller, we discovered that they were molecules or atoms, and then we were able to split the atoms and get electrons and protons, and we go to smaller and smaller, uh, and every step of the way, in some sense, we were able to kind of describe the physics of big things in terms of something that's smaller. And in a way, and as a result, we always tend to call that smaller thing more fundamental. So if we just kind of extrapolate from this trajectory, you can argue that hey, maybe like one day we'll finally find something that's ultimately fundamental. So I would say, sort of, I guess experimentally, it seems like there maybe is something that is really fundamental, but of course it remains to be seen, I think.
Huh. So are you saying like if we just keep going down smaller and smaller, eventually we might find something that is fundamental, or would it be like and just be turtles all the way down?
Well, I think there's hope that it will stop at some point. Like we haven't found much smaller things for a while now, like electrons. We haven't
We're
found.
so far away from the smallest point, though. Is there hope? I mean, in our lifetimes.
Okay, well, this is a practical perspective, right? Like for now, the practical perspective is like, okay, there's hope, that this is going somewhere. I mean, but of course, yeah, turtles all the way down is turtle through infinity, right? Like I don't think we'll ever get there, but there's hope, right?
We know
Yeah.
it's not goes all the way down. Well, okay, at least at a certain point, it has to become a vastly different kind of turtle. We know that.
Mikey, before you continue down that train of thought, you mentioned something about we're really far away from the smallest thing. Like, how do you know that? What does that mean?
Oh, that's actually the same point. So we can just do it at the same time. Um, like so. Okay, before I do that, I just wanted to like the question of like what is fundamental, right? This is like humans just love this question, right? Like for a long time, like as Tim mentioned, like in the Greeks, Democritus was the first person who hypothesized that like maybe everything is made from like just one kind of thing. And I think now that's like just the human desire for things to be simple, right? If it's true that like all of this complicated stuff we see can actually be explained by just a small number of building blocks like Legos, there's analogies for that, and there's like a human desire to want to believe that. Um, so I just wanted to put that up front, that to note that we have a human bias to want to believe that this is true. um, and then okay, so the question of why I said we're so far from actually seeing what's fundamental is that it's not that we know that there's some like distance where we look close enough and you'll see what's fundamental, but we know that there's like um, when we look at smaller and smaller and smaller scales, there's a certain scale at which like our basic notions of space and time kind of stop making sense. And that tells us that at that point, the description of nature has to drastically change. So like our description of these things as like Lego blocks should stop even making sense at that point.
What could you give a brief explanation of that? Like, why is that so? Just a really quick explanation.
Yeah, it's totally bizarre, actually, right? Like, actually, Tim, you backed me up on this in the history. Like, I would say it was like discovered pretty much by accident, right? Like the idea of Planck's constant. It was discovered as like, some kind of a ratio between the energy of a photon and its frequency, but this ratio kind of like was a hint that there's a certain distance, certain energy at which
No, but I mean, you have to add gravity in it, right? Like it's like first there comes quantum mechanics.
Well, I'm talking pre-gravity. I'm talking pre-gravity, right? Like when people just discovered Planck's constant, right? Like they didn't know that this mysterious number, was pointing towards some like fundamental scale.
Right. Yeah. I guess back in the days, people were discovering the wave-like nature of particles, and in order to describe the wave-like properties, they have to utilize a universal number, the Planck constant, to convert almost like particle-like property into wave-like property. Like how you can convert from like energy, something like a particle-like quantity into like the wavelength, something like a wave-like quantity.
It's really just a unit conversion, right? It's like converting from meters to kilometers.
Absolutely, yeah.
Like nature gave us this kind of mysterious conversion quantity very, very early on, like in the 1920s. There were hints that there was this conversion quantity to go from meters to like God's units or whatever you want to call it, and it's totally bizarre, and we didn't really even understand what it meant until like 20-30 years later, right?
Yeah, and I guess the magic really comes in when you look at gravity, basically. So a lot of times this conversion is just this conversion is almost taken for granted now. Like it's so ubiquitous. But
particle physics.
Right. But the moment gravity comes in, you see that gravity is dictated by mass, right? The more massive something is, the stronger the interaction. And because of this, you can actually convert, and also gravity has to do with distance, right? Like the farther away something is, the lower the gravity is. And because of this peculiar fact, and using this conversion factor, now we see that now there's a link between the strength of gravity and also all of a sudden, and also the scale, the size at which you're probing things. I think that's the interesting part. And as a result, it tells you that gravity actually indicated, like through this conversion of the Planck's constant, gravity actually gives you a scale, like a size. And then it roughly tells you that, hey, if you look close enough at that size, if you really zoom into that size, you're going to see something interesting, basically.
Huh. What do you mean interesting?
Right. So it's almost like this.
We're getting into it. We're getting into it early, but it's good.
Yeah, it's good. Yeah, it's good. I mean, it's sort of this prediction that which didn't used to exist before, right? Like why is there a limit on how far you can zoom in? Like who cares? You just zoom in more and more and more, right? It turns out that if you zoom in more, the thing that changes is gravity. Gravity's behavior changes, and it basically tells you that when you zoom into this scale, gravity's behavior becomes like we don't really have a good idea on what it would look like, right? But then gravity's behavior is going to become quite important, and at that point, like we
have a pretty good idea, at least classically. Let's not sell ourselves short here.
Right, sure. Like black holes might come in. Gravity becomes very strong.
They come in, right?
Right, and gravity becomes very strongly interacting. But ignore all that noise because all that interesting things coming in, things become not what they seem. Like the identity of particles can flip-flop, and basically all the things we know kind of start to break down a little bit. And when that happens, that tells you that, hey, if you're studying fundamental physics, something interesting is happening, right? Like you really want to zoom in that small and see what happens, because all the notions that we have about everyday about particles and everything break down. So something must be going on. So if there is anything that is fundamental, you gotta be looking. That's where you should be looking at. It's telling you that.
Okay, hold on. Let me try to unpack what Tim just said for Sahil, because I'm sure that was a. But okay, so do you buy that argument? Basically, what he's saying is that like, there is this fundamental minimum distance, right, where you know that all chaos breaks loose, because if you try to look at that distance, you create a black hole.
Yeah, I would agree with that.
Yeah, is that it? Might not be clear to the audience, right? But like because of quantum mechanics, the closer you try to isolate the exact location of a certain object, the more variability it is essentially in its location. And at a certain point, that variability is essentially equivalent to like a fluctuation, and that creates an enormous amount of energy. And there's a certain point at which, when you try to look at a particle too closely, there's so much energy that it just collapses into a black hole. So it's kind of like this region where we know this is kind of the minimum distance where you can call space, where it behaves as we would think space does. Yeah.
Yeah, and also, yeah, I think I like this train of thought, right? So the conversion factor comes in. First, you look at into a small enough distance, right? And then because of the Planck's constant, we have this conversion factor where length can be converted into energy, right? So when I zoom in really small, this really small size can turn into energy. And through Einstein's equation, energy is mass, right? And this conversion goes like this. The smaller the size, the larger the energy, right? And the larger the energy, the larger the mass, right? Einstein's equation. And the larger the mass, when you add in gravity, or at least the effective mass, when you have a large mass in a small space, it makes a black hole. So, right, this all comes together. Like the logic comes in full circle, and you need every piece of it. So I guess that's unprecedented. We never had this situation where that says the turtle has to stop, basically. This is a break on your turtle. So no turtles all the way down, all the way down until we hit that. But then, like, hell breaks loose, basically.
Or at least at that point, everything that led you to believe that there might be turtles has gone completely wrong, and you cannot rest on that assumption anymore.
I see. So if I were to like take a step back and go back to our original question, is there anything fundamental from this argument? Originally, if I look at classical physics or even like quantum mechanics, space and time are viewed as very fundamental. But you're telling me that because of gravity and because of going down to a certain length scale and you can't go below that, space and time are not as fundamental as we thought they were. Is that fair to say?
Yeah, it's almost like, so imagine when we think of space and time as fundamental, we think of it as like the canvas on which like you paint your reality, right? In a lot of ways, it's exactly true. But it has this weird feature that if you look at it closely enough, it basically rips itself apart. Like, what are black holes? Black holes are extremely violent distortions of our concept of a smooth space and a smooth time, right? It creates these like holes and arguably even like punctures in the surface. And so what we're saying is that this idea of a smooth background on which things unfold, if you look closely enough, it's got holes in it, like literal holes, like infinitely number of microscopic holes, like poked in it, probably.
Well, I think that might be true, but I don't think we literally know what it looks like. I think that's a good, probably like not a bad description.
But the indication that the physics tells us it looks like this is either an indication of physics or an indication of something totally just going wrong with the physics.
I think it's good to take a step back to look at everyday analogy where this happens, and we actually know what the answer is, so we can draw some inspiration to answer this question: what is fundamental, right? Like a good example, for example, is sound waves, for example, like air, like living in this room. You wave your hands, you feel the movement of the air, right? And so the things we feel in our everyday lives are the movement, sound waves, basically, like a jiggling of pressures in the air, right? And obviously, you don't see air molecule. And if you're a good physicist, you'll study the behavior of sound waves. You'll see that, hey, if you go to a higher altitude, the speed of sound might change a little bit and all that, right? And different temperature affects the speed of sound differently, and you can study all that, right? And then for a while, you might think of sound waves as very fundamental. Like it's what makes up the air. And you'll be right for a while. But until someone really gets some air together and imagine completely break down the physics. For example, there are multiple ways of doing it, right? For example, you can freeze the air. You can just put it in super cold temperature, and you see that the nitrogen, oxygen, whatever, they condense into like a solid or whatever, right, liquid. And then you'll be like, holy crap, like air is not what it seems. Or you can just zoom in with an electron microscope. Be like, dude, like I don't see sound waves. I just see a lot of molecules jiggling. That's another way of kind of totally breaking down what you're seeing. So in both instances, when we push the physics to its limits, we see that what we thought were fundamental, sound waves, were not fundamental. It's actually something totally different, like molecules. Who would like imagine you discover sound waves and you found different types of molecules like nitrogen, oxygen, hydrogen? That would be crazy. Like holy crap! Like it's not even just one type of molecules, right? And the different contraptions is totally unexpected. So this is sort of where we're at right now. Like I think we see particles. They look fundamental, but you can't really say they're fundamental yet, because precisely we're well aware of this analogy. Like, what if one day we're able to freeze all that into something crazy, or like completely destroy space-time, like what Mikey's saying, zoom in, all hell breaks loose, and maybe we'll see something else.
Huh. So when you say fundamental or approximately fundamental, like these like electrons, quarks, and the various force carrier particles, what makes you say they're like approximately fundamental, not like truly fundamental, but fundamental enough in some sense?
Everything looks fundamental until you look closer, right? Well, I mean, that's actually not obvious and not true, right? But I mean, you can kind of see the analogy. It happens in our universe a lot. Right? Like if you were looking at the solar system from far away, it might look like a dot, right? And then you zoom in, and you can see the structure, and you can zoom in, you can see more structure. It's not obvious that should happen. The fact that is true in our universe is kind of an amazing fact, but it seems reliable in a sense. So, yeah.
So what I'm hearing is that like if you weren't able to like observe it any closer, then what you see is effectively fundamental because it would describe your theory fairly well. Is that is that fair?
Yeah, I think so, and I think there's a bit of history to it, right? Like it used to be. I guess it used to be that physicists were maybe, I don't like to use this word, maybe a little more cocky. I guess we thought like the electrons. I think maybe 20 years back, people will be more inclined to say that, hey, maybe the electron really is fundamental, because all the equations that describes it, like the simplest equation or the most effective equations, in that description, you identify electron as a one unit of something, right? Like if you think of the electron as made of something else, you get a very wrong theory. Like it wouldn't be very useful, right? So I think people were very inclined to think like something like the electron, but like, yeah, probably it seems fundamental, right? And it doesn't seem like it's made of anything else. And you can also do an experiment, try to zoom in closer and closer and closer to see if there's like a hint of constituency, like it's made of something else. We don't see that, right? So people were more inclined to do that. But yeah.
Oh
yeah.
No, go ahead. You go ahead.
Yeah, but I think there's a flip side to that, right? So you have to before you make this judgment, like, oh, just because you don't see the constituent of something, can I claim it's fundamental? Before you say that, you have to ask yourself the question, okay? This is more like I guess from a statistics point of view, more like a Bayesian point of view, right? Like you have to look. You have to imagine yourself. Imagine yourself. I don't like to use this word. Imagine yourself. You're like God. Let's say, right? You're building this world, and you say, hey, if God were to make electrons composite, would we actually see it as fundamental? And it turns out that, oh wow, very much so actually. Like, even if the electron were not fundamental, there's a very good chance we'll still see it as fundamental. And just because of these, and in the same way, like there are very good reason to suspect that sound waves to us seems fundamental. Like I don't experience the individual molecules until I look really closely. So I think from that perspective, just because we haven't seen constituents of electrons doesn't give that much evidence to the fact that it's ultimately fundamental. That just isn't good enough, that evidence from that line of thought.
Huh. I mean, even atoms, I mean, the name itself implies some amount of fundamentalness because it meant indivisible. Is that correct, Mikey?
Yeah.
I mean, the
I
atom.
guess that's the question, right? So I guess the kind of point of like the culmination of this discussion is that things that seemed fundamental turned out not to be. So that's what makes it interesting. They turned out to only be approximately fundamental in the way that we just described right now. So the question is everything just approximately fundamental, or is there actually, if you get down, is there just one thing that truly is fundamental, right? So the notion of approximate fundamentality is kind of the whole discussion here, right? Like, is it turtles all the way down? Is it everything just approximately fundamental, or do you get down to, one mother turtle at the end? We know that we get down to something at a certain point.
So going off that train of thought, what if the mother turtle that you speak of was a string, like from string theory? Would that be the end of the story, or what's your guys' thought on string theory as like the most fundamental theory?
No, exactly. Yeah. So string theory is almost like you discovered a potential mother turtle before any of the data came in, but it just turns out that it kind of has all the properties that you would expect from a mother turtle, but there isn't any data to actually connect it. Because we're turtles all the way. If we're turtles all the way down, we're only at like the 24th turtle, but this mother turtle is down like number 60. So it fits all the properties that you would expect from a mother turtle. It turns out like that would have to be inevitable from a mother turtle, but there's no way to connect it exactly. And also, when you get down to string theory, it's interesting because at that point, this idea of things turning into black holes that we talked about, those problems are solved by string theory. There's a very clear description of what happens. The string gets larger and larger and larger, and you stop talking about points in space, you start talking about strings at that point. So it automatically cures that problem, which is like one of the major problems associated with this turtles all the way down thing.
No, but there's actually a flip side to this, and I think that's what makes this discussion interesting. There's a flip side, and that also comes maybe surprisingly, unsurprisingly, it also comes from string theory. String theory also tells us that strings isn't necessarily fundamental. I guess that's kind of the kicker, right? The way we study string theory is just a proxy for fluctuation. Think of it as a unit of fluctuation. And you can kind of think of it very much in a similar way, like sound wave is sort of a fluctuation of air pressure. So you can kind of argue that strings themselves, they are just a unit of fluctuation, but that doesn't mean that they are the thing itself, if that makes sense. Right? It's a way
the question of whether the fluctuations are more important or the locations are more important, right?
Yeah, and because of this black hole business, and that makes things so interesting. So the thing is, so fundamental, this idea of something being more fundamental, you can think of it as a one-way funnel, right? You always zoom smaller and smaller and smaller. It's a one-way street. You always go smaller, and if you go bigger, it's like the other direction. It doesn't work, right? Things that are more things that are more fundamental are smaller, just by definition, right? Kind of, almost. But string theory kind of throws a wrench into this because, like, at some point, if you try to zoom smaller, you kind of have more energy injected in the system. The system makes a bigger black hole, and the black hole gets
String
larger.
gets bigger.
Yeah, so basically,
You try to look smaller, the string gets bigger.
yeah, so as a manifestation of that in string theory, there are these things called dualities that relate strings, like that relates strings of roughly different sizes. Like so if you go to a string that's really small, you can think of it as really small, and you can also think of it as really large. So there's no sense in which the string basically is both small and large. So at that point, it's like, well, is this string made of something else? Like if you think of the string as really small, well, if you think of the string as really big, maybe it's made of something else. Or if you think of the string as really small, maybe it is the thing that's made up of everything else. Like which is which? It turns out that there's no good answer. Both viewpoints are valid. So it kind of throws a wrench into this whole idea.
Yeah, it's like you try to edge a seesaw to like find what's more fundamental, and then just like suddenly at a certain point just flips the other way.
So what I'm hearing from that is that when if you have a string, assuming string theory is correct in its description of nature, or at least like approximately correct, use that in quotes. If you pump enough energy into a string, it'll effectively grow larger because that'll form a black hole, which will get larger if you pump in more energy past a certain point. Is that effectively
And a
what
black
you guys
hole
think?
is a black string.
Yeah.
That's a
Yeah,
technical term.
Yeah, roughly speaking, yeah. If you look at the mathematics of it, yeah, you look at the size of a string, yeah, I think that's roughly right, right? The more energy, actually, the size get larger sometimes. It depends on the situation, I think.
So I guess like coming back to this question, so from what I'm hearing is like depending on how you look at what you're observing and how much energy you pump in and various different things, it changes the nature of the thing you're looking at. So my question to you is the thing you're looking at any less fundamental than the environment in which it's in, with the context in which it's in?
You can't really separate the thing you're looking at from its environment, right? Like, let's.
Yeah, man, that's
Yeah, it's tough because like in high school they always teach us like good science to separate, get good controls for your experiments and try to separate things as much as possible. But in physics, that's you can't rely on that ever.
yeah, that's a nasty problem in string theory actually, because like the act of observing it, like you can't like how do you observe a string? The string is the thing. Like you use another string or what? Like, and then when you use another string to interact with it to see that string, like what are you even observing? It's just and that's why in string theory this is actually a great difficulty. Like how do you define observing something? And a lot of times actually in order to define it, you have to be in a very particular space-time where you can send things to infinite far away. It's like the only way to actually have it correct is to have something. It's to imagine a really contrived experiment where you send something from really, really far away, from infinite time in the past, send it in, create a universe, something happens, and then the universe eventually kind of goes away, and you wait eternity, and then some particles come out, and then
No. That's just the perfect limit, right? Like
yeah, that's the perfect limit. Yeah. Yeah,
the only way you can actually talk about interactions is by imagining there's no interactions for a super long amount of time.
Eternity.
And then there's some interaction, and then there's no interactions for a super long amount of time after that.
Yeah.
Like the very act of talking about interactions requires us to make this kind of artificial separation between the experimenter and the experiment. And that becomes increasingly hard as you get more fundamental.
Yeah.
Yeah. So we're basically running at time, and so is there anything you guys want to say as the answer to this question? Just kind of taking a big step back and saying, is there anything fundamental?
Yeah, this conversation went very differently from I expected to, actually. But I think I think I kind of like shifted my perspective in a certain way, and I think it's that. String theory is awesome. String theory told us that this question doesn't make sense. Like it's kind of been this luxury that for the last 300 years, the idea of describing things in terms of simpler and more fundamental relationships has been fruitful. But if string theory is correct, then there's definitely a point at which this exercise in reductionism will cease in a very poetic way by kind of inverting itself, actually. So, you know, as Tim mentioned, we're very far from the quote-unquote string scale where these kinds of effects should manifest. So there could be several more turtles on the way to turtles all the way down. But I think we're starting to get a good picture of what the mother turtle looks like. And she looks like a mirror.
Yeah, I would say that, I guess, maybe not surprisingly, like many of our other episodes, like this question makes sense to some extent. Like we're not completely rejecting, you know, anyone asking these questions, but it only makes sense approximately, right? Like sure, we can see if, like for now we can say the electrons are fundamental approximately, but there's always this approximate caveat, right? I don't know, like 100 years from now, maybe we'll find that electrons are made of something else, and we can call that thing slightly more fundamental, at least for the time being. But it seems that ultimately, if string theory is correct, and honestly, even if string theory was not correct, even if there were some other physics that is correct, I highly suspect that this idea of just zooming in, finding things smaller, that makes up of larger things will probably break down, right? Like it's, and perhaps, and maybe we're already seeing some hints of that, and ultimately, you know, what's more fundamental? I think it's a human thought. It's just like it seems like that's just true as many of our other episodes. Like maybe we'll make more progress if we think more like what Mother Nature intended things to be. Like maybe this is another one of those not so well defined questions. There's just something out there. Not one thing is more fundamental than the other. Ultimately, they're just there. So.
All right, I'll take a stab at summing up my thoughts, and you guys let me know if this is on point or not. But I'll come from a slightly different angle, more I would say like humanities type of angle. So when I think about this, like if you were to tell me that there's a specific word or set of words or just the words we use in English language as fundamental, I would say like, are those words any less fundamental than the sentence in which it's in, the context in which it's embedded in? I'd also say mathematically, if you say the point, the origin is special, it's a unique fundamental point. And then I would ask you, is the space in which you need to characterize that origin point any less fundamental than the point itself? And so from what I'm hearing, if that's basically saying everything is fundamental, so nothing is fundamental. Do you guys agree or disagree with that?
I think that's a fair analogy on some level.
Yeah.
It's almost more than that. It's like everything is both fundamental and not fundamental, and yeah, it's.
Yeah, there are different viewpoints. Certain viewpoints are more fruitful for certain calculations and situations, but ultimately, these are all different pictures, I guess, of just one image, Mother Nature, and Mother Nature doesn't care, I suppose.
So, yeah, I mean, I just want to add one thing on top of that. Like, we're talking about this notion of like approximately fundamental. It's really like, is anything really true, or is everything just approximately true, right? It's kind of the same question. We're finding that like, and I think this is something people need to understand, is that like science doesn't look for exact truths typically. Typically, it looks for approximate truths in hopes that this exercise may or may not one day result in a exact truth if we're getting closer towards something, but that doesn't necessarily have to happen.
Yeah, I agree with that. So on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah, see you all next week.
Yep.
Yep.
Bye.